Alright guys, our focus for today to start chapter 6 will be how to find the antiderivative of a function. We use the symbol integral of f as the antiderivative of f. But before we begin further, let's go ahead and just take a few seconds to review differences between what we do now and what we've done before. So what we've done before is what's called definite integral, where you have a value on the lower bound and a value on the upper bound. And to find this definite integral, we just need to know what the antiderivative of f is, and then call it f. Call it big F. Once you know the antiderivative of little f, then what you do is you evaluate the antiderivative at the upper bound minus the lower bound, and that's how you find the value of this definite integral. The difference between a definite integral and an indefinite integral is an indefinite integral doesn't really have lower or upper bound. It's just an integral sign, and when you see this symbol stands for the antiderivative of little f. Okay, so this symbol stands for just the antiderivative of little f. And usually we call that big F plus c. Now the reason why c is here is because c is a constant, and if you were to take the derivative of this, you get little f, because the derivative of a constant tends to go away. But for now, just remember that when you see this symbol, it means you're looking for an antiderivative of little f. And that antiderivative is called big F plus c. Okay, that's the main purpose of 6.1, for you to be able to look at this and know how to find big F. Let's say if little f is the constant function 0, if that is the derivative, then what is the antiderivative of 0? Well, here is how we set up to find the antiderivative of 0, and the antiderivative of 0 is just a constant. So if the derivative is equal to 0, if this is the derivative, then the derivative has to come from a constant function, a function that's horizontal line. So big F has to be a constant function. So we say that this has to be some constant function. All right, some function. So big F is equal to c, some function, some constant function, because the derivative of that is equal to 0. So for example, specifically big F could be the function 5. Big F could be the function 10. But in general, we say that this just equals to c, some constant function. All right. What is the antiderivative of the function equals to k? Now k is a number. K could be 1. All right. F of x might be 2. F of x might be negative a half. F of x might be 10. So k is a constant. If your derivative is a constant, okay, what is the antiderivative of that? In other words, what is a function such that when you take the derivative of this function, you get these, right? So in general, if k is your derivative, then the antiderivative of k, which is represented by this symbol, is equal to k times x plus c. K times x plus c. And it makes sense because if you were to if you were to take the derivative of big F, then notice that you get K, because the derivative of big F means that this variable go away, and of course derivative of a constant go away, so you have K. And therefore, this is the antiderivative of that. Now, one thing I want you to notice is every time we find the antiderivative, there is always a constant that is involved, which we call that constant C. Alright? So far we look at two cases on how to find the antiderivative. First case is when your derivative is 0, and if your derivative is 0, then the function has to be a constant function. Right? When your derivative is a specific number, then the antiderivative has to be a line, some kind of linear line. Let's say if this was your derivative, then your antiderivative for that function would be something like this: 2x plus 10, for example. Because if you take the derivative of that, you get 2. And again, it could be 2x plus 10, it could be 2x plus 11. In general, we say 2x plus c because the last number could be anything. If you take the derivative of this, you do get 2. Alright? So we found the derivative of if your derivative is 0, then of course the antiderivative is a constant function. If your derivative is a number, then your antiderivative has to be the function of a line. If your derivative is a line, then your antiderivative has to be quadratic. So if this is your derivative, then this is the symbol for the antiderivative, and so we would get x squared over 2 plus c. This is our antiderivative, x squared over 2 plus c. The reason is because if we were to take the derivative of this, we would get x. Do it. If you do it, you bring this power down, it cancels out with the 1 at the bottom. C goes away, you get x. Alright, so in general, there's always a c involved. Now, there is a simple way to find the antiderivative if your derivative function is a power function. Given any power function, the antiderivative, this is the symbol for the antiderivative, can be found by basically taking the current power and adding 1 unit to it, and then dividing that by the same power, and then you add a constant c. For now, we don't know what that number is, so therefore we're just going to use the letter c for it. So make sure you memorize this formula to find the antiderivative of any constant function. Of any power function. Alright, so a few properties of derivative that you should know. First, if you want to find the antiderivative of the sum or differences of two functions, then you basically find the antiderivative of each one separately and then add them together. If you're finding the antiderivative of some constant times the function, then you can pull the constant in the front. Okay, pull the constant in the front. That's the second property. So let's take a look at this example. Example 1, find the antiderivative of 3x plus x squared with respect to dx. This resembles property number 1, so I can rewrite it like this: the integral of 3x dx plus the integral of x squared dx. Okay, and then 3 is a constant, so property number 2 applies. Pull out the 3 to the front. X is a linear function. We can use the power rule to find the antiderivative of x. And the power rule says take the current power, which is 1, and add 1 to it, makes it 2. And then divide it by the same number, which is 2. And then add c. Don't forget to add c. bring the 3 down. Okay, so that would be the antiderivative of this guy. And clearly, if you take the derivative, you will get 3x plus antiderivative of this guy. So we remember that we take the original power and we add one more unit to that, which is 3 now. 2, 1 more 3, divided by the same number, and then add c. Okay, add a different c, we'll call it c1. Maybe call this c1 and call this c2. And so let's combine this together and let's write it in a simplified form if we can. This is going to be 3 over 2, so 3x squared over 2 plus x cubed over 3. Now, C1 and C2, this is a number, this is another number. When you add those together, you will get a different number. And then we'll just call that number C. And C, remember, C is a sum of these two. We call it C. And they're just constant, so we don't know what they are, and therefore we'll just call them C. Okay? Same thing over here. We would need to apply property number 1 and then property number 2. But then we can actually do them together. So the antiderivative of cosine is actually sine. So you go 3 sine of x. The antiderivative of sine is going to be cosine. Negative cosine of x. And then each one of these would have a c, but when you combine them together, there will be a new c. That is the antiderivative for that. This problem is not an antiderivative problem. This problem is actually a definite integral. This is some number. It represents some kind of change, some kind of net change, and it could also represent the area. So to find this, to evaluate this, first we need to find the antiderivative for 3x squared. The antiderivative for 3x squared would be you add the original power by 1 unit, and then you divide that by the same number. Okay. Fortunately, these two cancels out. So the antiderivative is x to the third. So what you do is you take the antiderivative, you evaluate the function at 2 minus the function at 1. If you plug 2 in there, you get 8. If you plug 1 in there, you get 1. So this equals to 7. So that some net change is equal to 7. All right. This is the antiderivative again, because this is an indefinite integral compared to a definite integral. So when you see this, you're only looking for the antiderivative, and there could be thousands of them. All right, and that's why we have this letter C, because C could be anything. So therefore, there's infinitely many of them actually. So when you have sums of function, just take the antiderivative of each one separately. For example, what is the function such that when you take the derivative, you get 1 over x? Well, that function is ln of x. And then for this one, whenever you see radical function, turn it into a power function like this. Okay, and then use the power rule, which says that you just have to take the original power and add 1 unit to the original power. So 1 unit would be 2 over 2. That's 1 unit. And if you take that 1 over, that becomes 3 over 2, divided by the same number, which is 3 over 2. So going back here, the antiderivative of that will be x to the 3 over 2 divided by 3 over 2. But remember, dividing by 3 over 2 is the same as multiplying by 2 over 3. So I'm going to put 2 over 3. And then we're going to add c, because antiderivative, there are thousands of antiderivative. And therefore, we add the letter c to represent the fact that there could be a lot of them. All right? That's pretty much your note for chapter 6, section 1. I will see you guys on Monday.